Exam, bring it up front. How was it?
I want to hear from my name.
There's one problem where but
Overall good? I mean, you got the experience and understand now how to do those problems, which was the point, right? Okay. Okay, I'm not accepting any more, so if you haven't brought it up, you have one more chance. Okay. Now, we still have to finish up and prepare for the final exam. Where were we? It's been a while, it seems like.
Yeah.
Yeah, I know. And we only have 2 weeks left, so we have 4 lectures left.
you're doing something with standard.
So we were in thermodynamics. Let's start with that.
Yeah.
Chapter 18.
Yeah.
We talked about entropy. We correlated entropy with enthalpy to determine Gibbs free energy. We looked at what that free energy means in terms of whether or not something is spontaneous or non-spontaneous, right? And now we got right to where those were all under standard state conditions. Standard state conditions are what? 1 atmosphere, 1 mole, 298 Kelvin, right?
Yeah.
Okay, so those were the conditions. Then I said, well, different things happen, and whether or not you see something spontaneous or not may be because it's not under those standard state conditions, which are just areas that we could apply straight across. So if you recall, things like the node there, delta G node, that means that it's under standard conditions. But in non-standard conditions, how do you determine delta G, or the Gibbs free energy? And that's what we left off with, was we saw this equation here, which takes into account the standard free energy, and it also takes into account RT. R was given at the 8.314 joules. Make sure you know that's joules per mole to degrees Kelvin. Temperature, right? And this is also generally at standard state. So if it's at standard state, what would the temperature be?
Kelvin?
298. Okay. And what's this term here? Log Q. What was Q? We were introduced to Q.
It's a
The reaction quotient, which allows you to determine where you are in the reaction at any given time, right? So if I'm moving from reactants to products, or I'm past the equilibrium point, then Q equals, at equilibrium, Q equals what? K, right, remember? So if I'm at K, I'm at equilibrium. Okay. Also, from a Gibbs free energy perspective, when am I at equilibrium? When delta G is 0. Okay. So those two things correlate equilibrium to Gibbs free energy. Now, Q would tell me where I'm at. How do I determine Q? Partial pressure, if I'm dealing with gases, right? And if I'm dealing with aqueous solutions at 1 molar, then I'm dealing with molar concentrations. Okay, so we're going to primarily use this in the context of partial pressure on Q in relative to the reaction. So just to recall how we do that, that's the partial pressure of the products divided by the partial pressure of the reactants. Okay. Okay. So that's how we determine Q, and then we can correlate what Q is relative to what the new delta G is under those non-standard states. Because if Q is 1, then I'm already at the standard state. I don't need all of this. It should just be this right here. Right? Everybody see that? Okay. So this is now, I'm dealing with pressures, and when the pressure is not at 1, so I'm not at standard state, that's the change in the standard state conditions. Okay. And then we can correlate where we are here if we're at a positive delta G. Is that spontaneous or non-spontaneous?
Non-spontaneous.
Non-spontaneous, which means that if I'm not at K, I'm at Q, that causes delta G to become positive or non-spontaneous past that point of equilibrium. So that means that if I wanted to be spontaneous, it would be in the reverse direction towards the equilibrium. of the reaction. If the Q causes this term to be negative, then what does that mean? It's spontaneous in the direction the reaction is written. Does that make sense? And how these are correlated. And you can also clearly see that there's a potential here to correlate delta G at standard state with what? K, the equilibrium. And that's how we'll finish up this chapter with those two basic concepts. Okay. So if I look here at a chemical reaction, let me show you this again. This is really just a physical state change, but we're putting it in the context of like a physical, a chemical reaction where we have an equilibrium between water as a liquid and water as a gas. Okay? And over here, I have Q equals 1. Here I have Q equals 0. Those are going to correlate to different pressures. Let's see, this is my gas. This is my liquid, so the only partial pressure that's going to apply is going to be the H2O in the gas phase for the equilibrium constant, which now we're just looking at the reaction quotient. Okay? So with that being said, then I could put this amount in here to determine what my delta G is, and I could put this amount here in as a partial pressure to determine what the delta G is. So what would you expect it to be here?
0?
0. So under non-standard state conditions, when the partial pressure of this thing here hits 0.0313 atm, I now have equilibrium. So I don't have anything spontaneous going one way or another within this chemical equation. I'll call it that. Okay? If I'm over here, anywhere here down, then it would be spontaneous going in this direction. If I'm somewhere over here, then it'd be non-spontaneous going in this direction, but spontaneous going in the reverse direction. Okay, everybody see that? Which also changes the K here if I were to reverse that, right? Because now it's 1 over that.
Yes.
Okay, just to keep that in context. Okay, so that's what that chart's showing. So let's real quickly look at when I have 1 atm here, I have my standard conditions, and I plug it in here, and my delta G is equal to my delta G standard conditions, non-standard standard, which is 8.59 kilojoules per mole. Okay. Which also means what? It's non-spontaneous, right? Which is really important here because that would be the expectation that at room temperature, this would be spontaneous. But at standard state conditions, in terms of the pressure, it's non-spontaneous. So therefore, when would it be? It would be in this position right here, right? And before that. So when the pressure is lower than that. Okay, so let's take a look now. So the reverse here is spontaneous. That's kind of awkward because we're saying that evaporation is non-spontaneous, but the reverse now is spontaneous, which would be the opposite here. When you start seeing these things in the notes and in this lecture, I'm going to keep pointing that out because it's going to be confusing. It's going to say spontaneous. You're like, wait, we just said it's not spontaneous. It's the direction we're talking about. Okay, the direction of this here going this way is non-spontaneous. Going the reverse now is spontaneous. Okay, so I want to keep that in mind, and also keep that in mind when you're studying the notes because that will be confusing if you don't organize your thought process that way.
What was the 8.59 gotten from?
Plugging it into delta G.
From the
Which-
pressures that was given.
What's this term here?
As the R.
What's log 1? Put it in
Log
calculus.
1 is 0?
So then what's delta G equal to? And where do you
The
get that?
delta
From the
change?
table?
We
From
just
your-
got it from the table.
From whatever.
Oh,
you-
okay.
This is delta G under standard state conditions. It's now equal to delta G under non-standard state conditions.
Okay.
And this is something you can determine from a chart.
Okay.
Is that okay? Is that
Yeah.
maybe that helps others that didn't recognize that? Is that okay? Okay.
Thank you.
So now, if I look at the equilibrium here, this is basically when Q is K at 0.0313 atm, then I have this term here, which translates as my 8.59, and this becomes 8.59, so my delta G is 0 because it's at equilibrium as expected. And you could plug in those numbers. By the way, just to make sure, what are you plugging in R here?
8.314
8.314 joules, okay, per
298
And then this is 298, just so you know what's being plugged in. I'm just assuming that's already given.
Multiply
And I
all
just
of
want
that.
to make sure, sorry, one more time. The .0313 is from the chart, right there.
Yes.
So on, like on the test, they'll give it to us.
Mhm. Can you figure this out?
Yeah,
So what is this one given at?
as a equilibrium.
What is this? Equilibrium. So delta G is what?
0.
0. So then can I plug in and figure out what that was if I didn't know it?
Yes.
Absolutely, yeah. Just to make sure that your question comes across.
Right.
Okay. Oh, and so this is at equilibrium. So it's not favoring either direction.
Mhm.
Okay, now looking at 0.005 ATM, this is the second time we're seeing it non-standard conditions, but the first time we're seeing it prior to equilibrium. So we're coming down this way. And if I plug that in, this becomes a negative number, right? And this number is larger than this positive number, so I get a negative 4.5. So that means that it's spontaneous under these conditions
Yes.
going in this direction from liquid to gas. So under these conditions, you would automatically change your liquid to gas. That makes sense? Everybody see that? And that means it's spontaneous, what we're saying, evaporation going from this way to this way or down towards that piece there. Okay. And that's essentially this part of the section, this part of the chapter, this section. That's what I want you to know. Let's do a quick example. I have now, I'm putting this more into a real chemical reaction, not just a phase change. And I'm saying two nitrous monoxide and oxygen form nitrogen dioxide here. And I'm saying that delta G is negative 71.2 kilojoules. Okay. Which you could find from a chart too. And that means that this reaction spontaneous?
Yep.
Yes, if you look at this under what? Thank you, at standard conditions,
And also by the number of moles as well.
right? But let's not necessarily assume here that we're looking, so, okay, hold on. So Hurley just made a comment. What was your comment, Hurley?
That since all of them are gases, then the number of moles from reactants to products is less.
Okay, so what does that mean?
So that is spontaneous.
No. Where is he at fault? And this is huge. I love how he just correlated a past conversation and lecture with this one. But he's wrong in what he's saying, so let's dissect.
That's for entropy.
It's less.
What was that, Dieter?
That's for entropy.
Oh, entropy.
Entropy.
Yes.
And this is entropy of what? The system.
Right.
If you wanted to know spontaneity relative to entropy,
The
what
delta
do you
G.
need to know it from?
Delta G.
The universe.
Uh-huh.
Remember, delta S, or entropy of the universe, is equal to delta S of the system plus delta S of the surroundings.
Mm-hmm.
When delta S is positive, then it's spontaneous, which we later converted into delta G by making sure that we had all the system components of the entropy and the enthalpy. And that's where our delta H minus T delta S came in, right?
Okay.
So, and then that reversed it because it's a negative delta S times T of the universe.
Right.
So I love that you thought and how you thought about it. I just want to make sure it's corrected, and I wanted to enlighten everybody else into where you can become confused.
Right.
Okay, does that help?
Yeah.
Okay, cool. Okay, so now getting back through here, if I was under standard state conditions, what would my pressures be? One, what are they?
0.1, 0.1, 2 point.
Am I under standard conditions or non-standard state conditions?
Non-standard.
So therefore, how do I solve this problem, which is asking for calculate delta G?
So you gotta get Q.
Delta G equals delta G standard plus RT log
Right.
Q, right? How do I get Q?
Products over reactant.
I'm given this right here, I'm given this, right? Okay, so let's Here's my Q. This, right? Partial pressures.
Right.
And they were given. If they were 1, then how would I get this?
Oh, just.
Just look at delta G standard conditions.
Right.
Okay. Okay, so now I plug in here. This is just plug and chug kind of stuff, right? And I get this for my Q. Now that I have my Q, can I now solve for delta G? And remember, I was given delta G in the standard state conditions, but if I wasn't, I'd need a chart, which of course I would provide if you needed it on an exam. So is everybody comfortable with where we're at here? What's the other caveat here that I need to worry about? What's my
Oh,
equation again?
the most?
Delta G equals what?
Don't worry about the temperature.
Oh, negative
You already know the temperature here.
equals delta
It's,
G
it's
as standard
given at
conditions.
298. It's not in the problem, but because we're dealing with, it does not say anything, it's automatically under standard state conditions. We haven't changed that.
Oh, that one is kilojoules.
This is in kilojoules, and this is going to, and what is the R going to come out as? Joules.
Joules,
I have to
right.
adjust one way or another. That's
Okay,
the only
okay.
thing I want to point out now. Before, I wanted to do it before we got there, not after. If I do it after, then you just kind of roll through it and don't think about it.
That's what I did, yeah.
So here's my delta G, here's my delta G standard state in kilojoules, here's my R, my T, my log Q, and in this, at some point here, they just kind of threw in, so this is, they threw in your conversion between joules and kilojoules.
So if this isn't at standard state, they use 298 as the temperature?
Yeah. The only thing that's deviated from the standard state are the pressures.
Okay, so that's still.
Yep. So the T here is still under standard state conditions. And that gives me negative 50.7 kilojoules. And what does this mean here? No. That is spontaneous.
It's
right?
still spontaneous.
What's that?
It's still spontaneous.
It's spontaneous under these conditions. Okay.
I converted it to joules, it's fine either way,
Yep.
right?
Yep.
Okay.
What if I asked you from here, when would this thing be non-spontaneous?
Then set it equal to
You'd
0?
have to set it to the 0?
You would have to set this equal to 0 and then solve for whatever the Q would be.
Yeah.
And that would tell you your conditions from that point. But that would be your equilibrium.
Mhm.
So anything past that
No, it's
would be non-spontaneous. Okay. So what's the next one? We got another one here. What are we doing on time? Okay. So once again here, we're clearly not at standard state conditions because you have a variation in the pressures. And so you just solve for this the same way we just did there. Okay. So I guess the only thing you need to know is, this is the same reaction or a different reaction? Different reaction? It's this reaction here. And here's the delta G standard state. Okay. So with this, do we need to do this again?
No.
No? You guys know how to do this? This gives you another chance to do one at home. Okay, good. So I guess I could just put up the answer is negative 41.5 kilojoules. Okay? So that you guys can do that on your own. It gives you a good practice problem to do for the exam.
What was the answer?
41.5 kilojoules, negative.
It's in the back.
It's in the back. Okay, good. It's already in the book. Okay. Okay. You're almost done with thermodynamics. This is kind of really the last topic, which should be really smooth at this point. We're really just going to start looking at the equilibrium constant in relationship to delta G. Okay, so I'll let you read through this, take a whole bunch of stuff, but when delta G is 0, I'm at equilibrium. Okay, and so therefore the Q would change to what? Q becomes K.
Okay.
Oh.
Yeah,
Right?
at equilibrium.
Q becomes K.
Mhm.
Right? If it was 1, it would just be under standard state conditions.
Yeah.
This is good though. That's exactly what I want you to think about, the dynamics and what's happening. Rather you work that out now in your mind. It will make it much easier at home. Okay, so if I just make this 0, I can change that to K, and now I have my relationship between delta G standard state conditions and K. and then I just do a couple mathematical manipulations. Everything else is the same. That's it. That's the last topic you need to learn there. But what I will say is we probably are going to talk a little bit about whether or not K is greater or less than 0, and how that factors into the delta G number, and whether or not delta G is now positive or negative, and therefore spontaneous. That's it. That should finish off this chapter. Okay? So I just move this over, which then gives me delta G. Standard state conditions equals negative RT log K. Nothing miraculous there.
KC was
Nothing outside the realm of what you guys can do mathematically. Whoops. You have a question, Ruth?
I don't know, I was just trying to remember, the KC was concentration?
The K.
KC?
KC is, yeah.
Thank you.
So here are the 3 different scenarios where K is less than 1, K is greater than 1, and K is equal to 1. Okay. Once again, K, I'm saying you're at equilibrium. Otherwise, this relationship doesn't hold. So what does that mean towards delta G? Okay. So when K is greater than 1, or I'm sorry, less than 1, on this side over here of the reaction, so delta G is greater than 1 in the reaction direction that's written, which means that it's what? Spontaneous or non-spontaneous?
Non-spontaneous.
Non-spontaneous in this direction,
Right.
but spontaneous in the reverse direction, which is why this says reverse reaction spontaneous. So don't, I pointed this out earlier, that can be confusing. Okay. That also means that I would flip this around, so I'd have B gas equilibrium going to A gas in that direction, at this would then be spontaneous, because now my delta G would be negative. Okay. The next scenario, I have K is greater than 1, which means delta G is what?
It's negative.
Negative. So less than, or not negative, less than 1.
Okay.
Okay, we'll say here. And that means that I'm on this side of the equilibrium side, and it means the forward reaction, the way it's written, is spontaneous in favor.
Oh, because it could be 0 point, whatever, okay.
Once again, at standard conditions, though.
Right.
Okay. Because that's what I'm looking at, delta G standard here.
Okay.
Okay. And lastly, when K is equal to 1, then I now have my delta G is
Equilibrium.
equal to 0, and I'm at
Equilibrium.
equilibrium. Okay. Okay, let's walk it through. This is really the same thing I just said, laid out. So we're going to go through this unless you have questions. When K is greater than 1, reactants transform almost entirely into product. That means I'm on the right side of the equilibrium.
Right.
That's what's favored, which means that the reactants are favoring, the products are being favored. Log K is greater than 0. Delta G is less than 0. Reaction is spontaneous when K is greater than 1. That was the second picture to the right above from the last slide. K greater than 1. So I'm correlating that with this right here. That's this one. Okay.
Would the reverse reaction be non-spontaneous then, or?
The reverse would be non-spontaneous, absolutely.
And these are all I guess.
This is where you're dealing with K at equilibrium under standard state conditions. Is this reaction going to be spontaneous? Because it's you're dealing with a couple different things here in terms of the free energy, and also what else is involved here?
Quick question.
What's involved in here?
Oh, the RT.
Temperature.
Mhm.
At varying temperatures.
That slide you had up before, it had the delta G standard is less than 1, but this one says less than 0.
Yeah.
So if it's
yeah,
the
this is
same
less
as
than
positive.
0.
Which is just saying that this is
Negative.
overall
Negative.
negative.
Okay, so then the other one is not, right? That one.
And this is just delta G. This is it's kind of the same thing. Delta G would have to be less than 0.
Less,
here.
yes.
Yeah.
Okay. Thank you.
So, reaction is spontaneous in the forward direction. Same thing here, except for now when K is equal to 1, approximately, you have essentially an equilibrium. Because delta G now is about 0. And lastly, you have the reverse. So when K is less than 1, log of K is greater than 1, or I should say log of K is less than 0. And therefore delta G is greater than 0. And the reaction is now non-spontaneous in the forward direction, but it's spontaneous in the reverse direction. So wherever those equilibriums are, the direction you're looking at, that's what matters, right? Because if one is spontaneous, the other is non-spontaneous under those conditions. Unless you're at 0, then you're right at equilibrium. Neither are favored. You can kind of think of the equilibrium a little bit like potential energy. You're sort of at the lowest potential energy there. Remember, at the lowest potential energy, it's the most stable, so it doesn't want to go one way or the other, so to speak. You can think of it in those terms as well. So let's do a quick example here. Standard state, free energy of formation given, blah, blah, blah. You have this equation, you gotta have a delta G. So we're given delta G of formation. What's delta G of formation?
The lowest amount that it could. That it will
Of
form.
formation. I'm stating it. Delta GF is delta G of formation. What does formation mean?
That it forms the.
The formation of N2, H2, NH3, etc.
Right.
So these, do they take any energy to form? You get any free energy back from forming them? That's delta G, right?
Okay.
No, they just naturally form, right? Those are in elemental form. But in this case, I'm either going to get some energy back, or I'm going to invest some energy into forming NH3. That doesn't just naturally stay together the way N2 and H2, right? So in this case, they're saying that I'm getting negative 16.6 kilojoules per mole of NH3 made. That's the energy I'm getting out. That's the free energy I'm getting from the formation of NH3. So that's delta GF here, okay, under standard state conditions. So now can I figure out the delta G here? Yes. Yes, right. Delta G is just this times 2, and then plus 0. So that's my delta G. So now, use the standard free energy of formation given to determine the equilibrium constant for the reaction. How do I do that? Delta G standard state equals what? Minus RT log K. And what is it asking me for?
Just changing the temperature.
Equilibrium constant, and it's given me at the reaction at 25 degrees. So that's 8.314 times 298 times log K. And of course a negative in front. So that's this, and then I have a negative in front, subtract the negative out. This is a positive, I divide by 298, I get a number, I divide by 3.184, I get a number. Or can I do that? Can I simply divide by 8.314 here? And if not, why not?
Order of operation.
Units?
What are the units, Abs?
Oh,
Joules. What are the units given here?
kilojoules.
Kilojoules. I have to make that conversion, one to joule or the other to kilojoule, so that I can cancel those out. And then I'll be left with log K. I take the inverse log K of that number, and I now have my K. And I could figure out my equilibrium constant that way. Okay, so let's go ahead and take a look. This is what I was referencing. Negative here with a negative there, those cancel out. I move this to this side, so I get what do I have here? Negative delta G. So all I did here was move these two things underneath. And of course, this thing is a negative, so a negative is a positive. This divided by the 8.314 converted to kilojoules and 298 gives me 13.45. I take the inverse log of that, and I get 6.9 times 10 to the 5th. So what is this telling me again? What is this?
Formation. Delta G formation.
My equilibrium constant. Yes, it's very easy to get lost, which is
Oh.
why I point that out. What are
This
we
is
solving for?
Yeah.
So can I get any information, any other kind of information from here, just from the equilibrium constant? No, but I can't get information from this, right? What does this tell me?
Oh, that's spontaneous?
It's spontaneous, but I can't get it from there.
Right.
Right, I'm pointing that out because that's an instinct that you might want to try to do, but that's why I asked, what are we solving for here? Make sure we're aware. We're solving for the equilibrium constant, so it's not going to tell you that. Okay, let's try another one. Oh, did you, more, you want, Jenna?
Yeah, real quick.
Oh, could you show me the answer?
This one? 6.9 times 10 to the fifth? And I would definitely tell you to do this in your calculator. Make sure you get, it's easy to make a mistake in the calculator on this. Yeah, and the kilojoule to joule conversion is it absolutely, I think you'll get something like 0.013 as opposed to 113 point something or whatever if you don't make that conversion, and that will completely change your K when you inverse log that. Keep that in mind, make sure you make those things. On an exam, I would probably figure that out and take off a point, no big deal. But other people may not take the time to figure that out, and they just give you minus everything. So it's good to be able to do this and make sure you get the units right. Also, if you were ever doing this in reality for a lab and some of your lab work, then this would clearly be a big deal and nobody's checking it. You're the one checking it. And you don't want to make those kind of mistakes and try to publish it. It's hard to come back from something like this. Okay, so make sure you're aware of that and make sure you can do that in your calculator. Okay, next one. What are we looking at? So using the standard free energy of formation in your text to calculate delta G and K for the following reaction. This is essentially the same thing as we just did. So I'll leave this to you. You can go, let me see, do I have any? No, so you can just go to your textbook, get the delta G's of formation, figure out the delta G of this. Just make sure when you're getting that, you're looking at H2O as a gas, O2 as a gas, H2 as a gas. Make sure that your physical states are right in that formation information, because you probably will have solid, liquid, a gas of H2O, and those numbers are all different. Okay, so make sure that you use the right number. And is this also given, the answer is given in the back?
Yeah.
Okay, good, so you have the answer. Okay, if you can't get it, email me, I'll email you back, or come see me, and I'll explain it. Okay, but it's exactly like the last problem, essentially. Okay, oh, we have one more small topic, okay. Change of free energy with temperatures. You have the delta G standard state conditions here, and you see the little subscript T. That just means temperature. Why is this awkward? Seeing this here. You've already done this, right? We just didn't define it this way. We already did this where we looked at this equation when we first designed this equation and we dealt with the temperature. Remember that? This is essentially the same concept, right? So I have these at delta H's at standard state conditions, meaning 298, and here I have a temperature potential change. So this is what, but you saw that when we did this before, when we looked at, you saw, okay, at this temperature and above, it was spontaneous. At this temperature and below, it was non-spontaneous. Remember, we did those things with the delta G equaling to 0 at equilibrium. So this is kind of the same concept here. I think the only difference is we're using the standard states here, and I don't think we used the standard states initially. Is that right?
Right.
Is that, yeah.
Yeah.
Okay. So delta G, standard state conditions, is strongly temperature dependent. We already kind of knew that, and the T is right there. This is just representing temperature. And that, conceptually, there's nothing new here. Designation, slightly new, under a slightly different scenario, which is just that we now have standard state conditions that we're applying the temperature difference to. Everything else is exactly what we've already done. Okay? But so what makes this one even easier than what we did before? You can figure out these much easier, right, from a textbook or some other chart.
Mm-hmm.
Whereas if it was not under standard state conditions, then you would have to figure that out. Here you could just get these. Okay, we already know this. nothing new there, right? But now we're dealing with temperature, not standard. Anybody unclear of that? Should be pretty simple. So we are. Is it anything new there? You guys know this? And if not, do you have any questions on it? No, it's the same thing we did, right? Essentially. We just didn't do it under standard state conditions. The delta G were not standard state, and the delta S and the delta H were. Now they are. Okay? So clearly, as we saw in the past, in the earlier part of this chapter, that the delta G, whether it's standard state or not, is dependent on temperature. And when delta G is 0, then you can solve for the temperature is what we did, and we determined whether or not beyond a certain temperature would be spontaneous or not, based on the delta G being negative, right? So we saw it at 0. So that's something we did. So this is all, there's nothing new here. And I guess we'll just do a problem related to it. Sodium bicarbonate, or just sodium carbonate, no, sodium bicarbonate, can be prepared by heating up the sodium bicarbonate and forming sodium carbonate plus water as a gas plus carbon dioxide as a gas. Let's see, they give the delta H a formation of, and the delta S values, they must be somewhere, okay? So then we could figure those out. We're at 1 ATM, so that's okay. So then what are we looking for? We're gonna estimate the temperature at which this decomposes. Okay. Read the terminology there and make sure that it's clear what it's actually saying. Because it would be clearer if I changed that. What would make this more clear to what you're trying to solve for? Estimate the temperature at which sodium bicarbonate decomposes to products.
Information?
Spontaneous. When would it be spontaneous is essentially what it's saying, right? What temperature would make this reaction spontaneous? That's all it's saying. It just didn't say it that way. Why does that matter, and why am I pointing this out? To how I'm interpreting it and how you guys should. Because as soon as you hear the word spontaneous, you're looking for that, right? So then you automatically know that the delta G should be what?
Negative.
Negative, right? Otherwise, you're just kind of reading it, estimate the temperature at which it decomposes. What is it really asking for? Well, it's asking for whether or not, when is this thing spontaneous? Because you're looking to find a temperature that causes that spontaneity. So in order to do that, I know that at 0, what happens?
Equilibrium?
I'm in equilibrium. So then any temperature that now makes the delta G negative from that 0 would make it what? Spontaneous. Right. So you plug in for 0, delta G. And then anything beyond that, one way or the other, and you could just plug in and figure that out at that point. So what are we solving for here, and why did I walk you through that? Because once again, this is one of those word problems which now you guys are much better at than when you took 65 or its equivalent. But they still, the way things are phrased, come across a little bit different than maybe how it comes across when I'm giving the lecture. And so I want to make sure I correlate these things. So when you're looking on an exam, you read all this, and once again, there's a lot of stuff here, a lot of words, and those words become confusing. You just need to identify what it's saying, and then how should you solve it based on what you know. And the first thing I'd say is estimate the temperature at which this decomposes. So I'm looking at this reaction going this way. If I'm looking at this reaction going this way, I need to know when this would become spontaneous. And therefore, I'm asking what temperature is this going to be spontaneous at? And that means I set delta G equal to 0 because that's at equilibrium. Okay. From here, I can solve my delta H. From here, I can solve my S. What do you notice? That this is given in kilojoules per mole, and this is given in
joules
per Kelvin. I'm going to need to reconcile it. Okay. So let's see, we calculate those things, and then we calculate the temperature for this. So my delta H is that, my delta S is this, and I'm plugging, and I'll let you do, that's just products minus reactants. Don't forget the moles, right? Okay, the molar ratio. And now I'm plugging it into this equation here. If you recall, what's one thing I want to look at here is that this is positive. This is positive. So what does that tell us? Remember, I said we did this before, right? We just didn't do it under standard state. What does that tell us now? In terms of the temperature. At higher or lower temperatures, is this going to be spontaneous? Higher, right. This is positive, this is positive, this is a negative that this is positive. Remember we walked through that exercise, right?
Mhm.
So I could simply say, the higher the temperature, the greater chance this is going to be larger than this, which means that the overall delta G is going to be negative and therefore spontaneous. So I'm looking at temperatures that are higher.
Right.
I could already assess that from our previous knowledge, and now maybe you're recalling a little bit why I said we did this before. We just didn't do it under standard state. This is exactly what we did. We spent almost a whole lecture on. Okay, so I'm just going to plug it. Now when I plug in, can I simply say, oh, well, this is 337 times anything, even times 1. Is that going to be larger than 135.5? And if not, why?
No, that's
No, because
the joules.
it's in joules. Do not get fooled by that. If I convert this to kilojoules, what number does that become?
0.337.
0.337. That's a huge discrepancy.
Yeah.
That means this T has to be what?
Very large.
Very high, which is exactly the point. If I had just done this and I already identified as I did before I started this and said the temperature has to be high, and I realize at 1 it's already high enough, I know there's something wrong, which is why I'm introducing all of these things. You could see a lot more than you think, and you could figure out a lot more by looking at it and evaluating what you understand about the problem, and then you could quickly assess that there's no way that these things could be right in the same units if I could do a low temperature and still have spontaneity here.
Mhm.
Because a positive, you need a higher temperature to get that spontaneity. 1 Kelvin is a pretty low temperature, obviously.
Yeah.
Right? To quickly say, okay, something's wrong. What is wrong? The units don't match up. I match up the units and you'll see, you'll identify this much easier. So I just make this, I'm solving for temperature here. So I move, so you know, this is, what is delta G here? 0, because I set it equal to equilibrium. So then I move this over, from negative, negative becomes positive. I divide the delta H by the delta S, and I get my temperature here. Go ahead.
So you said set delta G to 0 because we are at equilibrium?
Or
Anybody help out?
we're,
No, that's, you're on the right track, but why? Go ahead, Taylor.
Because we're going for equilibrium, because anything less than 0 will be spontaneous. But, so 0 is like the closest thing to negative without actually being negative. We just
Anything greater.
arbitrarily
Whatever
chose
temperature
-1.
we get at equilibrium,
Anything higher.
anything above it will make this reaction spontaneous. That makes sense? So when I set this equal to 0, it's not spontaneous, I'm at equilibrium. But anything above that, in terms of the temperature, would then mean that the delta G would become negative and therefore spontaneous. And that's why I said, well, let me go back, because that's exactly why I pointed out here, estimate the temperature at which this decomposes to products. And then I said, what does that mean? It means that where is it spontaneous? And that's why I said delta G equal to 0, absolutely. That makes sense? Okay, so let's just throw in some numbers here. I have these two things here. You notice I converted this now from kilojoules to joules. Now you can see how much larger this is. This is 135.5 times 10 to the third divided by the 337.8. This should give me some fairly large temperature, 401.1 Kelvin. So anything above 401.1 Kelvin would be spontaneous, is the point. Does that make sense? Everybody understand the problem? And if you understand the problem, it makes it much easier, right? If you're just trying to memorize a formula and mix and match ideas to fit that formula, I'm essentially talking about the CB student to the BA student difference. Understanding the problem, you could just look at the problem and then solve it based on what you know. If you're trying to just memorize certain formulas, you could probably get by in the class with the CB, depending on whether you get a little lucky or a little unlucky on it works out for you. And then of course, if you don't understand the formula or the idea, that's when you don't pass. Those are the essential, that's how I define the 3 levels of students in the class. Okay, so this is going to be the same thing. You guys have the notes. Is there anything in here in the notes that you don't have?
No, everything's there.
You have the delta H and the delta S. This
Yeah.
is what I want to know.
Yeah, yeah.
You have these in your notes?
Yeah.
Okay, another problem to solve it. What's that? Yeah. So here, you're estimating the delta G at 400 K. So here they're giving you the temperature in this case, and then you're solving for delta G, and usually that means they're asking you whether or not this is spontaneous or not. And then a follow-up question that's pretty nice on an exam would then be to say, what would make it, where is the cutoff for spontaneity? What would make it spontaneous? So that you would assume this would come out as a positive delta G, and then you solve to figure out what it would be. Okay. So I'll let you work your way through that. And that's it. That's almost the last. We have one more chapter. This one is generally the most challenging. Hopefully I was able to break it down, tell you what I think is relevant.
This was the most challenging. I thought you were gonna say 19 was.
No, I think what I've seen in the past is that 18 is the most challenging for students, the thermodynamics. However, having said that, kinetics might be the second most challenging, and then the third might be electrochemistry, because there are a couple new things in electrochemistry, which is chapter 19. The good thing about it is the start of the chapter, which I want to get into today, is not new. It's all kind of easy, so I'll walk you through this. But this is electrochemistry.
That's what we're working today in lab. It was super simple, but the numbers were not given to the theoretical values.
Well, here, what I'm going to do early on in this chapter, and just today, remember we have 3 more lectures after today. So we're going to easily get through this material. I can go through it at a nice pace. What I want to do is get through the first part just to remind you a lot of Chem 101. Okay. Then we'll get into voltage potentials, which is what the bulk of electrochemistry is. All right, and we'll talk about a few things related to that. You'll see these things pop up in biological systems a lot, because you're looking at the electropotential of, say, something crossing over a cellular membrane, right? And you have that electrical potential, and you can figure out, can you transport something? What's that? Yeah. Electrochemical gradient, absolutely. So you look at the chemical components of each, and then the charges related to that, and you can get electropotential. And also, of course, you can look at the electropotential of, let's say, a battery, and going from one side to another, or voltage cells, voltaic cells, and we'll look at a couple different voltaic cells, and how to get the energy from one side to the other, and whether or not it's going to go in a positive or negative direction associated with the anode and cathode, et cetera, et cetera. So these are some things you're kind of familiar with and you're kind of not. I don't recall ever being introduced to this topic when I was an undergrad prior to this level class, with the exception of just hearing certain terms. So it will be, presumably I'm going to say it's going to be new for most of you, if not all of you, but it won't be overly challenging. I'm only going to give you some really simple concepts that you have to work within. Okay, and once again, throughout I'll point out different things. So starting this, these are the things that you already know, and I'll briefly walk you through it. The oxidation reduction reactions, assigning oxidation numbers, that's something that you have to recall. It may have been, that was one of the more challenging topics probably for you in 101, by the way. So hopefully at this point that will become a little easier. Oxidizing reducing agents, half reactions, if you recall those, putting them in. Another new component to this in terms of the reactions is, you guys looked at oxidation reduction reactions just on their own in water. We're going to look at them under acidic and basic conditions and how to balance them out. So that will be something slightly new, but once again, it's not that challenging. Just going to deal with adding some H2Os and hydrogen ions in acidic conditions because the H+, and in basic conditions, H2Os and OH minuses. It's nothing that will be that challenging. Then the new part will be talking about electrochemical cells, voltaic cells, things like that, the electromotive force, and how to determine this, and there will be some calculations, more quantitative related to that, and then the standard reduction potential. Standard means standard conditions and states, so we can compare things across and take that as a starting point to determine non-standard conditions, just like we did with thermochemistry. Okay, so this will be the newer area. A few new things and a few reminders will be in the first part of it. This will cover today, Thursday, Tuesday, and next Thursday. Okay, and that's how we'll close off the class. So we're in really good shape compared to most classes in terms of getting through the material. A lot of that is because I've condensed it a little bit more.
But we won't go through chapter 20.
Nope. That's
We
what
won't
is
have
that,
a final.
is that the, what is that? Radiation or something like that?
Yeah, it's,
Is it radiation and half-lives and stuff like
Please
that?
again.
Oh,
I actually wanted to do, so, is that in the syllabus? Is that why you asked?
Yeah.
It is?
but you said we did.
But I think early on I said we wouldn't do that, so we're not gonna get to it.
You said we wouldn't get to it. I just wanted to make sure.
I think, are the notes up on PropPass for that?
No.
no.
No, they're not.
No, they're not.
No.
Only on
Lecture notes?
If you're interested in that, I could give you the notes just for your own readings.
Yeah.
If you have an interest in that, and that could be beneficial to you. Whenever you're working in a lab, all of the things we do in here in biology, most of the experiments have to deal with radioactivity, right? So I attach like P32 to DNA and to other things, and that's how I could find either gel shifts where I look at things that could bind to DNA, for example. I just label P32 on one of the template, non-template strand, and then I look to see where that comes out in terms of running a gel. And I could see the binding potential of things. Or if I want to make a transcript. So if I'm doing transcription, I want to make a transcript, I use P32. And that integrates into the nucleotide, and I could see a variety of things. I could see if I'm in a region in DNA where it's melted, then I'll see single-strand thymines, and I could look at different, I'll put in permanganate, it will stop at a particular place, and as I make that, it's called abortive initiation, and I'll make that with
Start
P32.
coding.
So I need to understand how P32 works, for example. If I'm working on thyroid and I'm looking at, I want to see iodide uptake, right? Because that forms thyroid globulin, and that's usually if you have, and I think one out of 4 thyroid cancer are women. And so that's usually papillary thyroid cancer, and you have a sodium iodide symporter in there. And you cut that out if you get cancer in that region, and then you put in radioactive iodide, iodide 131, and that ablates all the cells. So once again, there's iodide radioactive and another radioactive source to take a look at and see how those half-lives occur and how long that could stay in your body. So if you're ever evaluating something and you want to figure out either for experiments through basic science or through clinical research like the I-131 example, then you need to have some sense of half-lives, and that's the degradation of the radioactivity. So how long will it be active, and how can that have adverse effects on other things, right? And in addition, you'll talk a little bit about fusion and fission, separating things, forming atomic bombs and things like that, and how those things. So that's where that chapter with radioactive iodide or radioactivity and half-lives and things matter. You probably won't need that at some point in your careers, depending on what you do. It's just good to know. So if you do want that knowledge, I could ask Said to put that chapter up, but we're not going to cover it as a function of this class. But that gives you a sense of what it was. Does that help a little bit, Jenna?
Oh, yeah.
Is that okay? Yeah. But I think in Jenna's case, she was just concerned that she might have to study more. Which is okay, because that's probably what I would say at this point in the semester if I was sitting in your seats as well. Another thing I have to study for. But that doesn't mean that others might not be interested in it, and then I could at least provide it for you, even though I won't have you study for it or prepare for it.
Yeah. It is interesting.
Yeah.
I just,
And it may not be interesting to everybody, I should point that out, depending on different people, different interests. Okay, so let's start this chapter, I guess this is 19, and we'll start with what you kind of already know, redox reactions. Where did we encounter redox reactions in terms of the chemical reactions we learned in Chem 101? How many chemical reactions did we learn in 101? Let's.
Oh, like 4 of them? 5?
5. Single replacement, double replacement, combustion, decomposition, and synthesis or combination. Those are the 5. One of them was not a redox. Which one?
That was the double?
Double replacement. And in the double replacement, we had 3 types of
3
reactions.
of them, yeah.
Neutralization, precipitation, gas forming. Came off of the unstable intermediate. Okay. That was not a redox. The other 4 were categorized as redox. What did redox mean?
The electron.
Electron transfer. Electron transferred from one thing to another. And that's what we're talking about. So that means we're not discussing double replacement reactions here.
So going back to 101.
Things like rusting of iron, bleaching of hair, production of electricity in batteries, all involve redox reactions. And what did I talk about? Electrochemical potential deals with things like batteries and voltaic cells and things. So that's why we're going to remember what kinds of things we talked about in terms of oxidation reduction, because that's going to play a role in determining electropotentials.
That's what we did today.
So, here we go. Synthesis, decomposition, single replacement, and combustion. So the only thing I left off there was double replacement. Okay. We'll get to that. This is the same. These are just the definitions. Whoops. Okay, so just to remind you, redox, oxidation half, reduction half. If something is reduced, it gained electrons.
Right.
If something was oxidized, it gave up electrons. That was the general sense of basic chemical reactions that we learned from a chemical perspective. From a biological perspective, it was a little bit different. Why and how was it different? Bigger molecules. So you can't just simply look at this big biological molecule and say this was gained or lost per se in it. So how did we do that? If it lost or gained hydrogens and oxygens, remember that? Gained oxygens, lost it. Look that up. I just want you to know it. It's not something we're going to necessarily deal with here, but it's something that you should have a sense of.
Right.
So from a basic general chemistry perspective, all we cared about was something gained. And by the way, when I said something gained, I have a chemical reaction here. I have reactants and I have products and an arrow. And those were primarily just single arrows, if you recall, right? Before we had talked a lot about equilibriums, which came up more with double replacement and acid-base reactions. How am I looking at this? What am I saying when I look at the reactions and I look at the reactants versus the products?
The gaining will be on the reactant plus.
I'm looking at the charges or the electron on these and how it changed over here. So if I have something over here that lost electrons, my charge on it is going to get greater or less?
Plus.
Greater, because I'm losing a negative charge.
More
It's
positive.
More positive.
Yeah.
That's maybe a better way to state it. And that if it lost electrons, it got a greater charge in terms of positive, negative.
Right.
Then what does that mean?
So it's a lead.
Oxidized.
Right.
Lost electrons. And if I go from the left side to the right side, and something gained electrons. So it's more negative now. What does that mean?
Reduced.
It was reduced.
Right.
What am I referencing? I'm referencing the thing that was in the reactants. It was either it gained electrons by the time it got to the product, then it was reduced. If it lost electrons by the time it got to the product, then it was oxidized. When I look at those two also, whatever, let's say this thing here was reduced over here, this was oxidized from here to here, that means that this is the reducing agent because it reduced this, and this is the oxidizing agent because it oxidized this. Just to recall some terms, that's why I say I just wanted to go over and make sure we call things before we get too deep into this chapter. Okay, so now I look over here and I see this reaction. What kind of reaction is this?
Formation.
Synthesis or combination. You use either term, right?
Yeah.
So see, just to recall, just when you quickly evaluate it. And this in its natural state is what charge?
0.
0. That's what I call in its elemental state. How do I know that? Because there's no charge next to it.
Right.
This one?
0 as well.
0 as well. In here, the overall charge of this formula is what? 0. Inside the formula, the magnesium is what?
2 plus.
2 plus, and the sulfur is?
2 minus.
2 minus, and you know that because that's one of those very simple metal and non-metal combinations, right?
Yeah.
So it's an ionic compound there. If it was a covalent compound, we'll talk about that. To place, we'll put up a pseudo system in order to place this that you've seen, but I'll recall. So that I look on this side, I see magnesium is 0. Over here it's 2 plus. What happened? Did it gain or lose electrons?
It lost.
It lost 2.
2 electrons.
Sulfur was 0, now it's minus 2. It gained those 2.
Right.
Okay. So this was reduced, this was oxidized. This did the reducing of this, so this is the reducing agent. This did the oxidizing of that, so that's the oxidizing agent. That's it. Okay, those terms that I put in perspective. And this is where you get the transfer of electrons, which is why we know that this is a redox reaction and not a double replacement. Everything I just said. Okay. Now, if you recall redox reactions, we also used to put them in half reactions, right? So, and I want to make this clear. I'm putting the oxidation half and then the reduction half. Okay, and that's what we're going to have to do for more complicated systems.
Oh, you can cancel out.
Yes, and we'll get to that. What I want to make clear, though, is by doing this, it implies, or at least visually, it looks like that these things happen at different times. But they actually happen all at once. The only reason for the separation is so that you could see what's actually happening in the reaction. So I'm going to put up this one, and then I'll put up this one. And this implies like this happens, and then this happens. In reality, this happens at the same time. They're not separated like this. This separation only allows us to not only see what's happening in the overall reaction, but in a more complicated overall reaction, it helps us balance it appropriately. So we're separating them into half reactions, but that's not how it actually works. This thing isn't sitting there like this and like this. They're all happening together. Just want you to keep that in perspective. So here, if I have magnesium here and this was oxidized, I have this over here. So when I say what was oxidized, I say magnesium, Mg. What was reduced, sulfur. This wasn't oxidized. This is the product of this being oxidized. For some reason, that comes across a little bit strange from 101 where people get confused by that. Hopefully this clarifies a little bit. This thing here, sulfur is being reduced. The product of that reduction is the S2 minus. Okay. And now when I look here, I have magnesium plus going to magnesium 2 plus ion. So therefore, this becomes this plus that. I start with this, and then as the oxidation of this occurs, these are my products of it. So here I'm adding the electrons and the number of electrons that were lost as a product. Okay. Inversely, in order to get this to go to here, to reduce this, I have to take the sulfur with the 2 electrons in the reactant side in order to form the S2 plus. Okay, so that's how I determine that the electrons in the half reactions for the oxidation half are in the product side, and the electrons in the half reaction for the reduction side are in the reactants. And even if you couldn't remember, I shouldn't say this, but say that gets a little confusing. You guys don't do this every day. When you go home, you're not thinking about this, and all of a sudden you come to an exam and you get confused. It doesn't ultimately matter that much as long as one's on one side, the other's on the other, because you're going to cancel them out. So don't use that unless you have to, but if you do have to, just make sure they're on separate sides when you eventually balance them out, and you'll be fine, because they're never in here. And in all fairness, when I'm grading these, for as much as I do look as much as I can, if this comes out nicely and the major parts of these look fine, I probably will not even notice that the electrons are on the wrong side. It's not the best way to do it, but if you get trapped and you don't know, and you still know how to solve the problem, then just make sure electrons are on one side and the other and they cancel. All right? Okay. Now, when I look at this here, I put this together and I simply say 2 electrons here, 2 here. I cancel those out. I pull this down. I get magnesium, sulfur, and magnesium 2 plus and S2 minus on the product side, and that's my total reaction. And that's what I get here, which should look just like this. So putting together the half reactions should give me the total reaction, which is exactly what I'm going to do because it's easier to balance the half reactions in more complicated equations. What else do you notice in here? Everything in there except for the electrons end up in the overall reaction, which means that when I do have spectator ions, which I don't have here, they're usually not included.
Right.
Okay. if they're included in what I give you, then you could just move them through accordingly, but they really don't play a role. So how, in a redox reaction, what would constitute a spectator ion?
Salt.
Something.
That would dissociate.
Yes, absolutely. So if I had like Cl here and here, and the Cl's minus on one side, minus on the other, it didn't change. That's essentially a spectator ion. There was no electron transfer with the Cl. Does that make sense? In that example. So whenever I had anything, and its charge on the left side is the same as its charge on the right, it's essentially a spectator ion in a redox reaction. Okay. So that example was easy primarily because it was an ionic compound that formed, right? The charge itself is the charge that you're looking at to see the number of electrons transferred. However, if it's a covalent compound, not so easy, non-metal and non-metal, then I don't have a charge to follow. So how do I figure out what actually happens in terms of its number of electrons that are associated, at least, with each ion or atom? So we're going to look at oxidation numbers and states. We definitely covered this in 101, I think, right? Okay, so I'm going to just recall this with you. Okay. So there are a set of rules. So these are, okay. Let's just take a look at the rules, and then I just want to emphasize it. The oxidation number of an atom in a free element is 0. Anything in its elemental state is 0. Okay. That's the charge. So if I have, in its elemental state, we do know some diatomics. So like N2, O2, F2, what would each one of those be in its elemental state? 0. Okay. All that's saying is this. I want to make sure this is clear because I know this is something that's brushed over quickly and not fully understood. So if I have F here connected to an F here, I have what am I putting up here? Valence electrons. Okay. In this, little line here is, what's the charge on that?
-1.
This.
Zero.
How? 0. What's the atomic number
because
for it?
yeah.
9? How many core electrons does it have? 2. How many electrons should it have left for it to be 0? 7. 1, 2, 3, 4, 5, 6, 7. Same thing with this one. So within the diatomics, each one is 0. That's the elemental state. You see why? I don't think I point out this clearly in 101. So this is just saying that anything in its free state or elemental state, whether it's diatomic or not, are there polyatomics? Polyatomics? Absolutely. We saw that with P, S, some of those in the metalloid areas, right? Those can be polyatomic, which means that they exist in their natural state in bigger complexes, like 4 P's or 8 S's together, all in their own, but still each one individually would be charged 0. Okay, unless it's complex to something else. So that's what this first part is in determining oxidation numbers.
What was the example of the polyatomic you gave? P?
P4, S8, things like that. So all of these, the diatomics in there, each one within the diatomic and each one of those, their charge is 0. They don't have any more electrons than protons. That's all that means. Rule 2. The oxidation number of a monatomic ion is equal to its charge. Na is +1. Its charge is +1. Its oxidation number is +1.